All right, ladies and gentlemen, welcome back to the wonderful world of physics here at VAHS. Today's topic is we're looking at momentum. Momentum is something that we had kind of talked a little bit about or seen when we were looking at Newton's laws. And you experience it almost every day when you're driving in the car, or basically every time you're driving in the car, not almost. You do experience it every day when you're driving in the car, when you're stopping or starting and things like that. And we're going to talk a little about what that is in a second here. So momentum is the product of the mass times the velocity. Really easy. We've got a lowercase p here, and that's going to be mass times velocity. Very simple. Now, because of the units then, the mass being the kilograms, and velocity is the meters per second, there are now the units then for momentum. It's a kilogram meter per second is kind of what that is now. Now, when we also look at momentum here, it says momentum has the special properties that in a closed system, it is always conserved and transferred, even in a collision. This is called the law of conservation of momentum. And that's an important thing for us to be able to understand and remember. So that the momentum, that when you, a great example of that was when you have two football players who run at each other. You've got a running back and you've got a linebacker, and they're running at each other, and one's trying to tackle the other. So whichever one has the greater momentum wins that battle then. And they would go in the direction then of the greater momentum. You see this when you play pool. Pool is all about momentum. You strike the cue ball with the cue and you give that ball a momentum. The ball has a mass and you give it a velocity. And then that momentum gets transferred then to another pool ball or another pool ball. So again, even in the collisions, the momentum is transferred or conserved then. It's not lost. So you're not losing any of it even though you've been in the collision. That's kind of what we see in the car when you're driving in the car as an example. You're driving in the car and you're on an icy road and you can't stop and you hit a tree. Then the reason why we wear seatbelts is so that the momentum doesn't get then transferred into you, then going into the windshield of the car. Our seatbelts then stop you from that. So same thing then as you slow down, right? Your momentum would carry you forward, which is again the reason why we wear seatbelts, is so that we don't slow down so suddenly that we continue to keep going. So the momentum then does get transferred or conserved. It's not lost. It's probably the best way of thinking about it, is that it's just not lost within the system then. So what we've got here then, the equations for momentum. Here's our, we don't necessarily have momentum on this one, do we? So we can't really deal with that one. Good? Let's look at the next one then. So here's our equations then for momentum. Momentum's down here at the bottom of the page. So what we have got then is, as we get down to here, momentum, there we go, is the mass times the velocity, again, kilograms times meter per second, so our kilogram meters per second is the units for that. We now then have a new equation then for mass, and we can write that, let's write that over here, so that then mass would be the momentum divided by velocity, and again, kilogram for that. And as we go up, then we've also then have a new velocity equation that we were learning about yesterday with velocity acceleration. So here then is our new velocity, or our new velocity equation dealing with momentum then. Velocity is momentum divided by mass then. And it is a kind of fairly simple kind of equation then with it. So one of the examples then that we can kind of see with that is looking at Newton's cradle. And you've all seen Newton's cradle before. So here's Newton's cradle then. Again, we've got the same size balls, the same mass of them and things like that. And you can then take them and move them around different ways. And so again, the momentum gets transferred from these two across to the next two, and the energy then is transferred or conserved then. Now what slows down, as it says the loss of the kinetic energy, it does slow down because of gravity. So gravity does actually absorb some of them, some of the energy and motion associated with the Newton's cradle till eventually it will stop. Now again, if we didn't have a gravity, that system would then, well, actually be floating and things like that, but if we lessen the effects of gravity, it would go for longer then. We could change it around and go to 3, and go 3 and 2, and again, showing you how the momentum from one set gets transferred to the next set then, which is kind of a really nice way of looking at all of that stuff. So hopefully this little demonstration does really help you in that process. So as we go back to this then, so here we go, we look at some of these problems then. For the most part, you're going to find that these are fairly easy to work with. And I think that you will kind of enjoy being able to take a look at them. There's not too many that aren't that are very difficult, but for the most part, we can just take a look at them. So again, what is the momentum there? We have got then, here's our mass, here's our velocity. So P equals mass times velocity. So we've got 0.5 times 1.5, and that then equals 0.75 kgm divided by s. There you go. For ones like number 6, drawing a picture does kind of help in that, because you're going to need to be able to look at what does it mean by the, and we kind of talked a bit about this earlier, that if you have arrows that are going with or against, sorry about that, as we look at arrows that are go with or against, then what do you do with those numbers and things like that? So take a look at that. Also too, notice that in this problem here, that you've also got kilometers per hour, and then how do you get that down into meters per second and things like that. So you do need to be a little bit more mindful as far as what's going on then with your units. It also does have that on the bottom of the equations page, is how to convert kilometers per hour into meters per second. So you're just going to want to make sure that you noted that. You would divide the kilometers per hour divided by 3.6 to get them into meters per second. Otherwise, why don't you then try the momentum partner problems and then the momentum homework. And if you have any questions, please make sure that you see me in class. Otherwise, enjoy physics, and we'll talk to you soon. Take care. Bye.